problem about getting the x average. Then you probably needed to select initial condition if you were using Heisenberg equation function, right?
Well, it wasn't actual. I misnamed it.
Oh, okay. Okay, let me collect your glorious works.
My paper's wider.
So the mini goal, minimal plan for today is just to go over the homework. And maximum is I have some plans for new material, but I don't know how it will go. Maybe it will take substantial amount of time to get through
We have to say.
I was trying to print a key, but it was a handwritten key, and the printer didn't have enough contrast, so it's not helpful. It's just not readable. What I'm going to do is to. You can guess what I'm going to do.
Giving us all 100s.
And
then we'll go over it.
Good guess. Good guess. No, what is a protocol? What are we going to do right now?
Grade each other.
Huh?
Grade each other.
Yes. So I don't know how sensitive you are. Just in case you are, I'm putting blank in front of you name. So that
What you all done grades?
Yeah, but yeah, I need it by 12. Some days it keeps letting it open, and it doesn't matter. I tell you. It's pretty easy.
What broke?
Something was written at the
Like using centers.
Oh yeah.
And I like breaks and measure break and now it's muscle break.
Not so much here or here, but right here.
Right here.
Fucking hate you.
Was that whole story in the web of my undergrad? Awesome. You see me moving yeah.
I think Kaylin might be a little upset.
I haven't had to look out for those since I was 13, man.
You've been doing it the whole semester.
Yeah. Well, you just lost the game. I don't know if you played that.
That's not even a thing.
It still is. When you started playing the game's forever.
Keep on.
Let me know if occasionally I redistribute you back your own work. In Hectic, I may.
Don't tell them, then you get the grade.
100.
Yeah, be generous.
100.
Well, that's definitely not mine.
You were so confident that now I'm getting doubts.
Oh man, you already gave him an F though.
F is not a grade. It means fantastic.
F for fun.
I think they got the same persons that graded last.
Yeah, it says Joey.
I was gonna say, that's not Joe.
No one got their own stuff? Okay.
I got Ben's.
Do not tell it. Well, after I don't know if you are close friends and you do not care, but there is an opportunity that someone in class do not like to disclose. So we are in the third chapter, right, on particles in the box, and there are like three sections: basic solutions like energies and wave functions. Second, predicting future time dependence, and there will be a third most attractive part about so-called density of states and nanostructures when we will talk about three-dimensional, two-dimensional boxes. I have expectations that you like this subject. I didn't print it, but it's really so. Next homework, probably we'll split it on smaller piece, and this one is like 5 minutes. Just run the code and print whatever comes on the screen, and we can make it due on Friday. So we do it on, and this is too early. This is probably due in 2 weeks. Okay, so here are the points. Be generous, find any opportunity to give extra credit. We want to brag to administration of the university that it is the best class in getting best possible grades. Help me in this. So 10, 10, 40, 10, 30, and 44 extra credit. So I am going to go over each problem with maybe some minor comments in case you do not know how to grade, if the grader is not sure about the solution. So the first one you just practice as functions, right? I think it should be minus x. No? Yes?
Question, could you group the dx and the x together as well, and then you get x times 1?
Or navigate my finger.
To the right a little bit.
Or is right.
There you go. Now, like, put it straight into the screen. Yeah. You have the x multiplied by x, but couldn't you take the parentheses and multiply the x by the d dx, and then get 1 from that, and then it would be 1 minus 1, I mean x minus that.
No. The convention is that if you, unless we are doing crazy things with propagating backwards in time, we assume that derivative acts on everything that depends on this variable and locate it to the right.
Okay.
So we need to practice the derivative of a proton, right? And for the second one, we were already doing it in class. So if you have differential operators, we always assume that there is a function at the rightmost side. And here we write it explicitly. So if there is a function here, the derivative applies to function once, and here we have derivative applying to product of x and this unknown function. And by practicing product rule, you have two terms. One, dx over dx times unchanged function, and second times is x unchanged times function, derivative of function. And you see there are similar terms, right? The first and the last are identical with opposite sign, they cancel. And the middle term just gives minus 5, right? And typically, if we are speaking on the language of quantum operators, we do not write this function. So we could remove this phi and tell that commutation position and derivative will be 1, meaning identity operator. If you've got minus 5, full credit, right? If, well, 5 and 5, but try to approach it to maximum. If something is wrong, give benefit of a doubt. Do not tell each other I owe you beer. Do not look and pretend that you don't know who is your grader.
Can we give them points for trying?
Huh?
Can we give them points for trying?
Of course, yes, yes. Be very gentle, generous.
You know, this is the first class I'm ever going to get an A for effort.
You know,
Well, you guys are my heroes because you are so brave to enter this class. You need to be rewarded just for this. So number 2 for 10 points, you just copy paste stuff from the lecture notes if you were taking something. So this assignment was designed in order to encourage you to take notes, so that they can help in making homework. So future is eigenfunction, exponential is eigenenergy, expansion coefficient. Expansion coefficient is projection of initial state onto eigenfunction. Input is initial state and set of eigenfunctions and eigenenergies. Output is wave function at any time and any position, prediction of future. So if it looks similar to this in the spirit, just pick. If it is very far from this, reduce our level. Okay, so your favorite problem. Everyone was so happy about. I'll go to empty thing and draw something. So how I would do this problem if I would have no time and attack of laziness. First, draw it graphically. So we know it's Gaussian function. We know it is centered on x0. And we know that if suppose we normalize it in a right way, suppose that someone did it for us, then area under this integral will be 1. Now, if we do multiply this function by x, right? So multiply two functions. Wherever function f equals x was 0, it will be 0. Wherever function Gaussian exponential was 0, so at minus infinity, plus infinity, it will be also 0. So the resulting function should come from cross axis here and asymptotically approach axis here and there. Also, here x is positive, and here we multiply everything by negative, right? Plus, minus. So we need to connect these 3 points. This, and this, and make it positive or negative here and there. Huh? Oops. Other reasons for these two wings will be unequal. Gaussian function is symmetric to the left and right. Then if you multiply it by x, these wings, they will be positive and negative, but by absolute values, they will be symmetric. So if you integrate such function, then the area under the curve, here it will be like minus something, and here it will be absolutely the same plus something. Okay? So if you take integral of the linear function being multiplied by, so that it will be 0, one needs to have it x minus x0. So that they both, center of the Gaussian and position where this function crosses the x-axis should coincide. So in this, if we match this condition, then the integral will be 0. And getting 0 is always good, right? So technical goal for this little math exercise will be to bring system of coordinates, to shift system of coordinates. Originally it was arbitrary here, and we want to shift system of coordinates here. And shifting of system of coordinates is just subtracting x0 from x everywhere, something like this. Okay, so we hope that multiplying linear function by Gaussian will give integral which will be 0. So it's one observation. Another one. What is the physical meaning of this question, of this problem? How would you interpret it? If it is not math, but physical chemistry or quantum theory. In average, at which position in space electron will be found, right? So we multiply position by distribution, and we need to get answer where it is located. It is very cool. Intuitively, it should be where the distribution has a maximum, right? So the answer should be x0. If you want to be super gentle, just see if the answer is x0. Just correct. Go to the next slide. If you're interested in protocol for solution, let's go through details. Okay, well, normalization, I'll skip it. It will be square root of 2 over pi. Probably everyone can do it. And if you get normalization, give whatever, 15 points. Now, here is the function that we need to take. Wave function didn't have 2 here, we put 2 because it is wave function multiplied twice, right? So multiplying 2 exponentials means doubling its power. Now, what if we shift our independent variable by x0? It will be fine with the integral itself, but here the x is not equal to x0, so we need to replace this factor in terms of x0, so x minus x0. So we need to look at x and find, x is actually x minus x0 plus x0, right? Hocus pocus. Nothing wrong, you just add and subtract. And after that, we can rename x minus x0 as a new variable. Z. Okay? Let me know if it is not clear, if you do not like this. The sign by not means like, yes, I do not like it. Also, if anyone is attempting to change variables, also give some plus 10, here plus 15. So after next logical step, after you come to an idea to identify new variable, you see here is something, here a bracket. We can open this bracket and consider this one integral as 2 integrals. One will have this new variable z dz e to the power minus z squared. Right? So it's same shape as we discussed before. It's Gaussian times linear. And second one has x0, which is not a variable, it's just a constant. Do you see it? So those are 2 different integrals. This one is Gaussian times linear, and this is simply Gaussian. And if you process this integral, you will identify that Gaussian integral here will be equal to square root of pi. And here there is a square root of pi from normalization, and they will cancel. And square root of 2 will appear because of this trick here. So after you take this integral, you will get x naught. And here it is the stuff that we were debating on the previous slide. So it is minus and then plus. So it is a symmetric function integrated from minus to plus infinity, which will be predominantly 0. Okay, so full credit if there is a right answer, and find any opportunity to lift the grade. Also, if some of you may go to grade school and TA, so if you're bored while grading, just write some jokes to whoever you're grading. Whew. Okay. Yeah, here are details if you're curious, but I think you already got the idea. How to get x naught. So in order to put here not 2z but only z, e to the power minus z squared, I need to submerge the square root of 2 under the differential. Okay, but I will send these notes if you really are curious. And as Alex told, all these integrals, like Gaussian times x, Gaussian times x squared, are online. They are also on the little chart of mathematical expression that I distributed before. So this is just a little instruction what to do if you suddenly found yourself on the inhabited island and you need to take integrals. But human civilization knows the answer, and you'll find it easily. So, problem number 4. Oh, give me a little feedback. Were there substantial progress on those whom you were grading? Or it was just blank, or?
They're trying.
Trying, okay. Okay. So, problem number 4, it is what we were doing in class to support by your observations the uncertainty principle. So if we look back for the product of uncertainty of position and momentum, it will be constant plus quadratic function. Right? So if you see something similar to quadratic function, just put it. And the meaning of this work is that no matter whether you go forward in time or backwards in time, uncertainty will increase. So everyone should be absolutely perfect with the problem, right? So you do some manipulations in order to fit summation of 3 coordinate functions into boundary conditions, right? And by matching the boundary condition on the left, you get that we do not have our coefficients in front of cosine will be always 0, and then we match the boundary condition on the right edge to get coefficients in front of sine function. And the critical thing is to also select the rate, how quickly fringes are accumulating. Okay? So argument of sign should be natural number, pi times natural number. And then if you need this rate, how fringes are developing, you just divide by n by the size of the box. And then you plug it in and get n pi over size of the box times x, which is really important that not any wave vector, not any momentum is allowed inside the box. There are only discrete set of so-called quantum numbers. We will go to this idea again and again in any application. So this is very common trend. In any quantum problem, there are quantum numbers. So some observables are allowed to have only specific values. Done?
About 6.
No, just if you see something, give maximum. It will be part of in-class effort at the end of the week. Huh? 40 is maximum.
Okay.
So please add together your generous grades and put it at the front page and circle. I will just glance through and likely approve everything.
19 out of 100.
That's right.
Problem from 1 is fine. So if each is full frame, accumulates to 100. If you get everything done and plus extra grade, it's usually 140. But 140%. I'm just counting so that 100% is needed to get in there. And the rest is safety. Or what happens if car crashes?
Airbag.
Airbag, yes. What is the total? Huh? Please.
20.
Okay, I have to announce that all class does really well in homeworks. Do you have any time for anything else? Or are we doing this time?
15 minutes here.
Okay, 15, whatever, 13. So, you all can read it. But it is an interesting observation. So, if you do have box without walls, which will be our free particle, right? Rubbed electron. Then when it has zero momentum, it doesn't move anywhere, and its energy is literally zero. You remember, right? It's like p square over time, and you replace p by constant times wave vector, h square k square. And if k is equal to 0, then energy is literally 0. But do we have the same thing for the particle in the box? Can the energy be 0? What do you think? Like, if your electron doesn't move anywhere, Well, in average, it doesn't move completely, but you still have fringes. It means that it bounces back between walls, right? Is there such a state of electron in a box that will have zero energy? What is your opinion, intuitively? So, no. Why?
Because electrons are always moving.
Okay, but in the free space, there is a possibility to have zero energy. I'm just trying to confuse you, you're right. So if there are walls, it must bounce forth and back. So even if it is a lowest possible energy, you have seen that lowest eigenfunction has this half fringe, which means that it does move. So presence of fringes means there is some motion. And we'll go through equations which are very simple. This is the simplest problem in quantum theory. The previous one, free space, was not the simplest. So you're already heroes. Now we are covering the simplest problem. So if we look, and you can do it, you may already, you may have seen it, or it is, all derivations are ridiculously simple. They are like half line, one line. But it is an interesting heads up to look at. So even if it is the lowest eigenstate of electron in the box, the energy will be larger than zero. And another observation, if you try to squeeze energy will try to increase. So this is some people, in respect to other degrees of freedom, not electronic, it's correct for any quantized degree of freedom, including the nuclear motion. And this effect is known in respect to infrared spectroscopy, Raman, so-called zero-point energy. So even if you, when you were thinking about everything intuitively, or maybe went through some elements of thermodynamics in whatever freshman class, you had an idea that if you freeze everything, if you put temperature to zero, there will be no motion, and energy will be zero as well. It sounds intuitively correct, right? But it is correct only if your degrees of freedom are classical, if there are no quantum effects. If you realize, if you take into account that there are quantum properties of particles, there is a zero-point energy. The energy of a particle, which can be electron, proton, something more complicated, will be more than zero at absolute 0 Kelvin. Okay? And we will see soon. I may just get too excited and forget to point your attention on this, but you may make a note. 0-point energy is non-zero. So I'm going to give the summary of, so we do have 3 sections in this chapter. Ground state properties, eigenstates, eigenvalues, then prediction of the future, and then multi-dimensional boxes. So here is a little summary of the first section, but after the summary I will go into more details so that you feel comfortable, and if one day you need this knowledge once again, why may you need it? In which instances you may need particle in the box? First, if you are studying quantum dots. So Ben will need it. If you will study quantum dots of thin film or quantized nanostructures in the future. Second, if you will need to pass some cumulative exams for some other things, or if you will need to go through subject jury. So very likely that it will be questions about box will be assumed the simplest possible questions, and they will be asked in any exams. Here in class, we will deal with numerical things or with some prompts. Okay. Normalization factor is square root of inversely proportional to size of the box, right? And the wave vector, meaning everything except x, we can call it k, is inversely proportional to the size of the box, pi, and natural number. So it's important that it is a discrete set. Also, originally we start to look at any solution in form of the de Broglie wave, like exponential to the power of with accumulating phase. So originally we started with exponential solution, but then due to boundary condition, it does reduce to trigonometric shape, and you see that eigenfunctions are real, which is really comfortable. Right? What else? Discrete. So it is the concept of quantum numbers. So it is a standard feature of any quantum problem that energy is allowed to take only certain values. It's like going on the highway, and instead of being forbidden to travel quicker than 80 miles per hour, there is like discrete. You are allowed to drive 10 miles per hour, 20 miles per hour, 30 miles per hour. But if you drive 1 mile quicker or slower, you will be ticketed. So discrete. What else? Well, this momentum energy scale is actually what comes into energy. And if you plug in Planck constant times this stuff into equation for kinetic energy, you will get the thing that depends on Planck constant, mass, pi, which are constants, number of this eigenstate, and then size of the box. So it is what we were talking at previous slide. The energy of quantum state depends on size of the box. And it is inversely depends. So the larger the box, the smaller is energy. Or opposite, smaller the box, the larger the energy. Right? Anyone trying to come to the door? Oh. I will put number 1 here, because we do not have solutions if n equals 0, right? We excluded them because they do not match the normalization condition. If n equals 0, it is what we were doing on the lab. It will be just horizontal line given no probability for electron to be anywhere. So we need to exclude it. And then the lowest possible state is when n equals 1. So we put n equals 1 here, and we have this energy. We see this energy is not equal to 0. Some of you may feel bored at this time, but it is a great discovery. It is a strongest implication to modern civilization. So people are getting, I don't know, Louis Bruce got Nobel Prize for looking from different angle on this equation. So if your box, remember we were once, in the past we were talking about what can be particle in the box, like oligomers of conjugated polymers or confined pieces of semiconductors. Right? So if you manage to fabricate a piece of semiconductor, silicon, not continuous, not large, but smaller and smaller and smaller, you can tune the energy. So when you tune the energy, it means, we will go to more details, but tuning the energy also meaning that one can tune the transition energy upon photoexcitation, which means you can tune the color. You're aware of the dye. There are molecules of different colors, and you can use them for paint or for if they try to emit light upon applying voltage, one can use them for light emitters. But typically, you have different molecules for different color. Here, one can have the same chemical composition, just of different chunk, different size, and generate different colors, which is really great for engineering. You do not need to study different materials. You have just one material of different thickness. And then you do any device that either emit light or convert light into electricity or some other stuff. So this 1 over L square is a really big deal. It's a good idea for maybe surprise quiz next time. Put empty boxes and invite everyone to produce. I don't know if I will have energy, but to do steam. But so mass, Planck constant, number of harmonic, and then size of the box. So Planck constant means that unless you are on atomic size, this effect is not important. So if you take piece of semiconductor of size of like 1 foot or 2 feet, there will be no quantum effects. One needs to really go to nanometers. Mass, sometimes one needs to use different mass, not actual mass, but so-called effective mass, because interaction with other particles make electron to behave as if it would have different mass. And most important is dependence on size. Yes. Here is a little illustration about the tuning of so-called gap of the optical transition in silicon. So it will be equal to whatever it is in infinite plus contribution from the quantum confinement. And this is called Bruce equation, or with some additional terms. And if we would be, bless you. If you would write this equation with understanding of location-induced semiconductors 30 years ago, you could get some prize for it. Now it is too late. Someone already claimed it. And typical size example. So this one is about 1 electron volt, which is about at the edge of near infrared. And if your quantum particle is the size of 2 nanometers, it will be about greenish. So one can tune over the spectrum. Good. We will postpone beginning of the lecture to the next time because we are out of time. Thanks much for your energy that you invest into this course.
What do you think, John? Should we try
What are your options? Something like French fries,